In the beginning of every great mystery, there is a moment when certainty begins to tremble, and the universe itself feels like it is breathing in a strange, uneven rhythm. For generations, we believed we understood the first page of the cosmic story. We imagined the universe bursting into existence in a single incandescent moment, a flash of unimaginable heat and light echoing across eternity. That story once felt solid, almost comforting in its simplicity. But now, subtle cracks shimmer across its surface, and something deep beneath our understanding begins to shift. It is as if the very fabric of knowledge is whispering that the truth is far stranger, far more intricate, and far more unsettling than we ever dared to imagine. When scientists peer into the depths of space, they expect to find confirmation of what they already know. Instead, they are confronted with hints of contradictions, clues that behave like shadows slipping between the fingers of established theory. The universe, in its silent immensity, seems to be telling a different story, one that refuses to fit neatly within the borders of the Big Bang narrative. These fractures appear not as loud explosions of revelation but as gentle, persistent ripples that disturb the surface of cosmic certainty. Each ripple carries a question, a doubt, a quiet suggestion that the truth may lie far beyond our familiar boundaries. Imagine standing at the edge of a vast cosmic ocean, watching waves roll in from a horizon so distant it defies comprehension. Each wave carries fragments of ancient light, whispers from epochs long before galaxies existed. In those whispers, scientists now detect inconsistencies, tiny deviations that grow more alarming the closer we look. These deviations are not errors, they are signs. They tell us that the story of creation we have trusted for nearly a century may not be the story the universe is actually telling. The weight of this realization lands slowly, almost imperceptibly at first. Small anomalies begin to gather like storm clouds, each one subtle enough to dismiss, yet impossible to ignore when seen together. They come from different corners of astrophysics, from measurements of expansion to observations of ancient stars, from the structure of early galaxies to the behavior of cosmic background radiation. None of them alone can topple the Big Bang. But together they create a tension, a quiet, relentless pressure that feels like the beginning of a seismic shift. As this pressure grows, the scientific community finds itself caught between awe and uncertainty. The universe has always been a place of wonder, but now that wonder carries an edge of fear, as though something enormous and unseen is turning beneath the surface of reality. There is beauty in the mystery, yet there is also danger, in the possibility that we may need to unlearn the very foundations of modern cosmology. When a story so deeply rooted in our understanding begins to falter, the ground beneath us feels less stable, and every piece of evidence must be re-examined with fresh eyes. The night sky becomes a vast archive of unanswered questions. Every star, every galaxy, every whisper of radiation becomes a clue in a cosmic investigation. The familiar becomes unfamiliar. The stable becomes fluid. The universe, once thought to be understood in its broad strokes, becomes a labyrinth of hidden passages and shifting walls. But this is the essence of scientific discovery, the moment when old maps fail and new pathways demand to be explored. In the silence of deep space, contradictions linger like faint echoes of a forgotten truth. What we once believed to be the beginning may simply be a chapter, or perhaps a transition, or even an illusion shaped by our limited perspective. The cracks widening through the Big Bang narrative do not signal the end of knowledge. They signal the beginning of a deeper search. They challenge us to look beyond simplicity, beyond comfort, beyond the familiar glow of a single cosmic explosion. This is the moment when creation feels open again, raw and unbounded. The mystery deepens, inviting us to step forward, to question everything, and to follow the fractures until they reveal the unimagined. As we stand on this threshold, the cosmos ceases to feel like a solved puzzle and instead becomes an ancient riddle carved into shifting stone. The questions rising from these cracks are not small, they pierce into the heart of existence itself. What if time did not begin the way we think it did? What if the universe carries memories older than the Big Bang? What if the first light we see is not the echo of creation, but simply a trace of some deeper, hidden cycle that we have not yet learned to name? These possibilities unfold like a cinematic panorama, expanding far beyond the borders of what we once considered possible. The deeper scientists dive into these anomalies, the more the universe begins to resemble a grand illusion, an exquisite yet deceptive tapestry woven from assumptions that once felt unbreakable. The familiar timeline grows thin, stretched to its limits by data that refuses to conform. The more we search, the clearer it becomes that the universe may not be a simple story with a clear beginning, but a sprawling epic filled with revisions, mysteries, and forgotten chapters waiting to be rediscovered. And with every new clue, the cracks widen, revealing a breathtaking truth, that the quest to understand our origins has only just. The story of the universe's birth has long been told as a grand symphony of fire, a radiant eruption that marked the beginning of everything we know. For decades, this image has shaped our imagination, an unimaginably dense point of pure energy exploding outward, igniting the cosmos with blinding brilliance. Scientists described it as a moment where time itself awakened, where matter first took shape, and where the seeds of galaxies were sown in a single violent heartbeat. The narrative was elegant, powerful, and deeply poetic, a simple origin for a complex universe. But beneath its beauty, something now feels uncertain, as if the flames that once illuminated our understanding have begun to flicker. When we imagine the Big Bang, we picture a blazing, expanding sphere of heat tearing open a dark void. We imagine the first seconds as a storm of particles, forces, and raw chaos sculpting the architecture of reality. That image has guided generations of researchers, textbooks, documentaries, and classrooms. Yet today, as we look deeper into the cosmos and gather more precise data, those bright images begin to blur at the edges. The fire that once explained everything now seems to hide unanswered questions within its glow. The universe's beginning was never observed directly. It was reconstructed from evidence, like archaeologists piecing together ancient ruins. The relics of that supposed explosion, radiation left behind, galaxies speeding outward, patterns frozen into space, formed a coherent, powerful story. It was a story that made sense. It was a story that felt complete. But as scientists continue peeling back layers of cosmic history, cracks appear in this narrative, hinting that the universe's fiery birth may not be the whole truth. There is a growing tension, a cinematic shift in tone, like realizing a familiar tale has missing chapters. Imagine the early universe as a furnace of unimaginable heat. Temperatures soared so high that atoms could not exist. Spacetime was warped and turbulent. Within fractions of a second, forces separated, matter crystallized, and the foundations for everything, from stars to consciousness, were laid. This sequence is often told with certainty, but the deeper we probe, the more this certainty begins to tremble. Observations from our most advanced telescopes now reveal structures too old, too large, too organized to fit the time frame provided by this fiery origin. It is as though the universe is whispering that something came before the blaze, something we never accounted for. The Big Bang Theory gained power because it tied together multiple clues. The expansion of space suggested an explosive beginning. The cosmic microwave background appeared to be the cooled remnant of that primordial fire. The distribution of elements, hydrogen, helium, and lithium, seemed perfectly aligned with the aftermath of an early high-temperature environment. These clues were woven into a narrative so compelling that it became the central framework of modern cosmology. But the universe, in all its vastness, rarely offers stories without twists. As we zoom out mentally, picturing the universe stretching in all directions, we feel both awe and unease. The galaxies drifting apart at accelerating speeds do not simply move. They escape from us as if responding to a force we cannot see. The more we observe, the more this behavior contradicts the idea of a neat and predictable expansion after a single explosive birth. The original tale of fire does not account for this runaway motion, nor for the invisible driver behind it. The cosmic fireball begins to feel like the opening scene of a much larger, more mysterious film. In the standard picture, the universe expanded smoothly from a tiny, blistering seed. But what we find instead are ancient galaxies that should not exist, arranged in ways that defy the expected timeline. They shine too brightly, contain too many heavy elements, and appear too structured for their supposed age. It is like discovering skyscrapers in a civilization that should still be living in wooden huts. These anomalies strike at the heart of the fiery birth story, suggesting that the universe was far more mature far earlier than we believed. The cosmic microwave background, the afterglow of the primordial fire, was once seen as the ultimate proof of the Big Bang. Its faint, uniform glow stretches across the sky like a relic of creation. But even this sacred relic is now a source of tension. Tiny fluctuations in its temperature reveal patterns too subtle and too specific to fit smoothly into the original fiery expansion model. The more precisely we measure it, the more it seems to hint at a pre-Big Bang structure, a hidden architecture underlying the supposed chaos. Picture the first moments after the explosion, a seething plasma of particles colliding at near-light speed. This furious dance laid the groundwork for the atoms that would later become stars, planets, and eventually life. But new observations show that this dance may not have been as chaotic as once imagined. Instead, there may have been order, patterns, or unknown forces guiding the early universe with a precision we have yet to understand. The story of fire begins to feel incomplete, as if the flames we picture conceal an older script beneath them. Scientists once believed the Big Bang marked an absolute beginning. But today that idea feels less certain. The fiery explosion might not have been the beginning of everything, it might have been the beginning of something new emerging from something older. Some theories now propose that the universe may have existed before the blaze as a different state, perhaps a contracting cosmos, a timeless field, or a quantum haze beyond our comprehension. The Big Bang may have been a transformation rather than a creation. This realization casts a long shadow. If the fiery birth was merely a transition, then the comforting simplicity of "the universe began here" fades into uncertainty. The cosmic story becomes deeper, stranger, and infinitely more complex. Instead of a single fireball, we may be looking at cycles, collisions, or processes woven through infinite time. The flames that once symbolized the beginning may actually be the middle of the story. The emotional weight of this shift is enormous. For nearly a century, the Big Bang's fiery imagery shaped our understanding of who we are and where we came from. It gave us a sense of cosmic clarity, a single spark that unleashed everything. Now, as the evidence darkens the edges of that flame, we feel both awe and fear. Awe at the possibility that the universe is far more mysterious than we imagined. Fear at the realization that our most cherished cosmic story may be collapsing under its own brilliance. The fire of creation still burns in our imagination, but its light now casts unfamiliar shadows. Behind that glare, something larger looms, something waiting to be discovered. And as we prepare to follow the evidence deeper into the unknown, one truth becomes clear: the universe is not done surprising us. For nearly a century, the foundations of the Big Bang theory have rested on a collection of clues, ancient, silent, and scattered across the cosmos like relics of a forgotten age. These pieces of evidence once fit together with remarkable precision, forming a narrative so compelling that it became the accepted origin story of everything. But as with every great mystery, revisiting the evidence reveals something deeper. The clues are not as simple, not as complete, and not as unshakable as they once seemed. The universe, in its quiet vastness, may be telling a different story hidden between the lines of these cosmic artifacts. The first great pillar of evidence was the expansion of the universe. When astronomers observed galaxies drifting away from us, they interpreted the motion as cosmic fingerprints left behind by an explosive beginning. The stretching of space, revealed by the redshift of distant galaxies, became the first major clue in the story of universal birth. It was as if space itself were exhaling, pushing everything outward from a central moment of unimaginable intensity. This expansion was so persuasive, so visually striking in the data, that it became the backbone of the Big Bang narrative. Yet the more precisely we measure the universe's expansion, the more the numbers begin to whisper inconsistencies, subtle hints that something in this elegant interpretation might be incomplete. The second pillar was the cosmic microwave background, the faint afterglow that fills the sky in every direction. When discovered, it was hailed as the smoking gun of creation, the cooled, faded residue of a once blazing universe. This radiation seemed to confirm the fiery early state proposed by the Big Bang, a thermal imprint frozen into the fabric of space itself. Scientists mapped its delicate temperature variations, interpreting them as seeds of future galaxies. But as our instruments grew sharper, these patterns began revealing strange asymmetries and irregularities that did not match the predictions. The once perfect evidence became a subtle puzzle, suggesting structure before the universe should have been capable of forming any. The third pillar was the abundance of light elements, hydrogen, helium, and traces of lithium, scattered throughout the cosmos. These were thought to be forged in the universe's first minutes, when temperatures were high enough to drive nuclear reactions but not yet cool enough to allow heavier elements to form. The observed ratios seemed to align perfectly with the predictions of early universe nucleosynthesis. Yet these numbers, once considered pristine, have begun to show cracks as well. Measurements of lithium in particular refuse to align with theoretical expectations, stubbornly resisting correction even after decades of analysis. The chemical evidence, once a triumph, now reads like an ancient script with missing lines. All three pillars still stand, but they no longer stand without question. They resemble ruins eroded by time, powerful, iconic, yet beginning to reveal the possibility of a deeper truth beneath their surfaces. The expansion is real, but its speed contradicts itself depending on how we measure it. The cosmic microwave background exists, but its tiny deviations hint at something before the supposed beginning. The elemental abundances fit a pattern, but not one that aligns perfectly with the original predictions. Imagine walking through a vast archaeological site. Each artifact uncovered tells part of a story, but none reveal the whole narrative. A cracked vase, a fragment of a mural, a weathered inscription. They paint a picture, but they also leave room for interpretation. This is what the evidence of the Big Bang has become. Not lies, not mistakes, but incomplete relics of a universe far more intricate than we first believed. Galaxies moving away from us do not necessarily mean they were once packed into a single explosive point. They could also indicate a different kind of expansion, a stretching driven by forces unknown, or even by cycles of contraction and rebirth. The cosmic microwave background might not be the leftover heat of creation but the echo of a deeper transformation, the residue of a universe reshaping itself rather than emerging from nothing. The light elements may not be the product of a singular fiery moment but of processes occurring over a longer, more complex timeline. As scientists examine these clues more closely, they find themselves standing at a crossroads. The once cohesive story built from these pieces begins to feel like a puzzle forced to fit a predetermined shape. The data still holds truth but perhaps not the truth we assumed. Each piece seems to tug the narrative in a slightly different direction, like stars drifting away from the gravitational pull of an old belief. The deeper we look, the more these evidentiary pillars begin to feel alive, shifting under the weight of new discoveries. Expansion suggests a beginning, yet early galaxies appear too mature. Microwave radiation suggests an origin, yet its patterns imply earlier order. Elemental abundances suggest early fire, yet their ratios hint at complexities we do not yet understand. Every clue carries both confirmation and contradiction, a duality that keeps us suspended between certainty and doubt. This uncertainty is not failure, it is revelation. Science thrives in these moments when the ground trembles beneath established theory. The tension between evidence and interpretation becomes a gateway to new understanding. Each inconsistency becomes a torchlight revealing unseen corridors in the labyrinth of cosmic truth. The universe does not hand us complete stories. It offers fragments, light stretched across time, radiation frozen in space, elements forged in ancient heat. And from these fragments, we attempt to reconstruct the origin of everything. But the universe is older, stranger, and more layered than our models can fully capture. Perhaps the most unsettling realization is that the story we built from this evidence was not wrong, but incomplete. The pillars were never false, they were simply partial glimpses of a much grander structure. The Big Bang may still be part of the universe's story, but not the beginning of it. These clues may not be evidence of an explosion but of a transition, a transformation, or a process that began long before the fire ignited. As our telescopes peer deeper and our equations grow more precise, the evidence does not crumble, it evolves. And in that evolution, a new story begins to take shape. The story of a universe far more mysterious than we ever imagined. For decades, the expansion of the universe seemed like one of the cleanest, most reliable pieces of evidence in cosmology, a smooth, predictable stretching of space that could be measured, mapped, and explained with almost mathematical elegance. Astronomers imagined galaxies drifting apart like glowing embers from a dying fire, carried by the slow breath of an ever-growing cosmos. The motion was gentle, graceful, and expected to follow a predictable rhythm. But the deeper we looked, the more that rhythm began to falter. The universe wasn't just expanding. It was expanding in a way that shouldn't look like this, too fast, too uneven, too contradictory to the neat equations scientists once trusted. In the early days of cosmic measurement, the assumption was simple. The universe began with a tremendous burst of energy and had been slowing down ever since, stretched thinner by gravity and time. It made perfect sense that after an explosion, the outward motion would gradually lose momentum. But when researchers studied distant supernovae, brilliant detonations that serve as dependable cosmic markers, they found something unsettling. Instead of slowing down, galaxies were speeding away faster than expected, as if pushed by an invisible hand. The universe wasn't decelerating, it was accelerating. And that single discovery shook the foundation of modern cosmology. Imagine watching a film of an explosion. You expect the fragments to scatter rapidly at first, then gradually slow as they move outward. But now imagine the opposite. The fragments start moving faster and faster the further they travel, as if the emptiness between them is pulling them apart with increasing strength. This bizarre reversal defied every intuition scientists had. Nothing in physics predicted such a thing. If the expansion was accelerating, something profound, something completely unknown, was influencing the universe. This unexpected acceleration introduced a strange new force into the story, something that repelled rather than attracted, something that pushed rather than pulled. Scientists named it dark energy, a term that conveyed more mystery than understanding. It acted like a cosmic puppeteer, pulling galaxies away from one another with silent, relentless determination. But naming it didn't solve the riddle. No one knew what dark energy was, why it existed, or how it could behave with such overwhelming influence. The expansion that once looked smooth and logical now appeared chaotic and unexplainable. The more precisely astronomers measured the expansion, the more contradictions emerged. Structures in the universe, superclusters, filaments, voids, did not behave the way they should if the expansion were as uniform as once believed. Some galaxies appeared to be moving too fast for their distance, while others seemed oddly slow. Patterns in the cosmic web hinted that expansion varied in ways not accounted for by any existing model. It was as though the universe followed rules we hadn't yet discovered, rules that refused to align with the simple Big Bang narrative. As scientists attempted to map the rate of expansion across time, they encountered another unnerving inconsistency. The expansion rate seemed to differ depending on how it was measured. Observations of the early universe suggested one value for the rate. Observations of the modern universe suggested another. The numbers did not match, and the disagreement grew more severe the more accurate the measurements became. This conflict didn't merely challenge one equation, it challenged the coherence of the entire cosmological model. Picture two clocks ticking inside the universe. One measures the expansion from the earliest light available. The other measures the modern expansion using nearby stars and galaxies. In a perfect universe, the clocks should agree. But these clocks diverge in dramatic fashion, as though the universe is telling two incompatible stories about how fast it grows. This discrepancy, known as the Hubble tension, creates an enormous crack running straight through the heart of cosmology. It suggests that either the early universe behaved differently than expected, or the current universe operates under physics we don't yet understand. Even more troubling, the expansion seems to respond to regions of space in unexpected ways. Some distances suggest stronger acceleration than others. Some voids seem to grow faster than theory permits. Some galaxy clusters resist the tug of expansion more than gravity can explain. The cosmic landscape no longer resembles a calm, evenly stretched fabric. Instead, it appears warped, uneven, and dynamically influenced by forces that do not appear in our textbooks. As the puzzle deepened, some scientists began to wonder if the expansion was being misunderstood from the beginning. What if space wasn't stretching in the way we imagined? What if the acceleration wasn't caused by a mysterious energy but by something more fundamental, a flaw in our understanding of gravity? Several theories propose that gravity itself may behave differently on cosmic scales, bending and shifting in ways that depart from Einstein's equations. If true, the expansion of the universe might not be a reaction to a primordial explosion at all but a manifestation of deeper laws that govern spacetime. Such ideas, once fringe, now carry weight. Modified gravity theories attempt to adjust the rules rather than introduce new substances like dark energy. Others suggest that what we perceive as acceleration might be an illusion caused by large-scale cosmic structures. If the universe is uneven or filled with massive voids, our measurements could be distorted by perspective. But even these alternative explanations struggle to account for all the anomalies. Every new telescope, every new survey, every new data set pushes the mystery further. The James Webb Space Telescope revealed galaxies that behaved strangely at distances where expansion should follow predictable patterns. Their brightness, structure, and distribution seem to argue against the simple notion of a universe stretching uniformly after a single explosive event. Instead, they hint at a cosmos more dynamic, more layered, and more unpredictable than our current models can capture. This growing disorder in our understanding carries emotional weight. Scientists once believed they grasped the essence of cosmic expansion, tracing it back to the fiery moment of the Big Bang. But as contradictions mount, the universe feels less like a system we can chart and more like a living, shifting entity resisting reduction to simple laws. There is awe in this uncertainty, but there is also fear. A fear that the story we built around the Big Bang might be unraveling in ways we cannot yet repair. The expansion that shouldn't look like this opens the door to radical possibilities. Perhaps the universe is older than we think. Perhaps it went through cycles of expansion and contraction. Perhaps it emerged from a previous cosmic era, carrying leftover structures that influence the current rate. Or perhaps the expansion we observe is only one layer of a deeper process, just as the motion of the ocean's surface is only a hint of the vast forces beneath. When we confront the accelerating, inconsistent expansion of the universe, we face a fundamental truth: our cosmic map is incomplete. The equations that once guided us now wobble under the pressure of data that refuses to conform. The universe stretches not like a slow breath but like a mystery unfolding, revealing deeper complexities with every measurement. And as the expansion continues to defy expectation, one thing becomes clear. Whatever the universe is doing, it is not following the script we wrote for it. The story of cosmic growth is changing before our eyes, pushing us toward a new understanding of where we came from, where we are going, and what forces truly shape the vast, unfolding darkness around us. It begins like a quiet disagreement, the kind that scientists initially brush aside with calm curiosity. Two methods for measuring the universe's expansion rate, both respected, both rooted in decades of research, should produce the same answer. The cosmos, after all, has only one true rate of expansion. But as the measurements became more precise, the numbers refused to align. What started as a small numerical gap widened into a chasm, dividing the scientific community into two camps staring across a growing cosmic gulf. This conflict came to be known as the Hubble tension, and it behaves less like a minor inconsistency and more like a full-blown contradiction woven into the fabric of the universe. On one side of the debate stands the early universe, represented by the cosmic microwave background, a faint afterglow emitted when the cosmos was only 380,000 years old. Using this relic as a starting point, researchers calculate the expansion rate by applying a model of cosmic evolution known as lambda-CDM. According to this method, the expansion should be slow and steady, with a rate that matches the universe's early behavior. On the other side stand nearby galaxies and exploding stars, objects much closer and much younger in cosmic terms. By measuring how fast these galaxies recede, astronomers calculate a different rate altogether, one noticeably faster. These two numbers are not close. They diverge in a way that cannot be explained by simple measurement error. Imagine two witnesses in a courtroom recounting the same event. One describes it calmly, methodically, based on old records and memories. The other offers vivid, immediate testimony, insisting that what is happening now contradicts the old account. Both witnesses are credible, both insist on their accuracy, and yet their stories cannot be reconciled. This is the nature of the Hubble tension. The early universe tells one story, the modern universe tells another, and the difference between them is too large to dismiss. The cosmic microwave background suggests a slower expansion, a universe growing at a measured pace, consistent with the predictions of the standard cosmological model. But Type Ia supernovae, stellar explosions used as standard candles, indicate a faster expansion, as though the universe were rushing outward with unexpected urgency. When these measurements are compared, the results diverge by a margin far greater than statistical uncertainty should allow. Each new dataset, each new instrument, each new measurement adds confidence to both numbers rather than closing the gap. The tension becomes even more dramatic when viewed through the lens of precision. Modern instruments like the Planck satellite can measure the cosmic microwave background with exceptional accuracy, mapping its temperature fluctuations down to millionths of a degree. Meanwhile, supernova surveys, improved distance ladders, and local measurements refine the nearby expansion rate with increasing reliability. Both sides improve, both stand tall, yet the contradiction grows sharper, like two parallel lines that should converge but stubbornly refuse. As the numbers diverge, so does the narrative. If the early universe and the modern universe disagree so profoundly, then something fundamental may be wrong with the model connecting them. It raises chilling questions. Did something unexpected happen between the early and modern universe? Is the standard model of cosmology missing a crucial ingredient? Or are our assumptions about dark energy, dark matter, or the fabric of spacetime incomplete? The tension draws scientists deeper into the puzzle. They test whether the cosmic microwave background might be subtly distorted, perhaps by unknown particles or fields influencing the early universe. They test whether supernovae might be evolving in ways not previously understood. They examine distance measurements used to calibrate cosmic distances, checking for hidden biases. But each time a potential flaw is considered, evidence pushes back. The disagreement does not shrink. It persists with eerie resilience. Some propose that dark energy may have changed over time, acting differently in the early universe than it does today. Others suggest that dark matter may have exotic properties influencing cosmic expansion. More radical ideas propose that gravity itself may behave differently on large scales, requiring modifications to Einstein's equations. If any of these theories prove true, the implications would be profound, rewriting the rules of cosmology. The emotional weight of the contradiction is impossible to ignore. In scientific fields grounded in precision and mathematical elegance, a direct conflict of this scale is both thrilling and terrifying. It suggests that the universe contains secrets far deeper than we imagined. The Hubble tension becomes a crack in the cosmic mirror, reflecting not only data but the possibility that our entire understanding of the universe's evolution may be incomplete. Picture scientists gathered around competing diagrams, equations spreading like branching rivers across whiteboards. Each side has compelling evidence, each side is supported by observations of extraordinary quality. Yet the two stories cannot be merged. The tension becomes a riddle whispered by the universe itself, a riddle that grows louder with each new measurement. As new telescopes come online and advanced surveys scan the sky, the conflict intensifies rather than fades. More accurate local measurements confirm the faster expansion. More precise analyses of the cosmic microwave background reinforce the slower expansion predicted by early universe physics. The gulf widens like a wound in the cosmological model, demanding explanation. This disagreement is more than a scientific inconvenience. It is a doorway. It invites the possibility that the universe is stranger than the standard model allows. Perhaps the cosmos experienced an unknown phase of acceleration in its youth. Perhaps new particles or forces shaped its early evolution. Or perhaps the Big Bang model, as beautiful and powerful as it is, describes only a portion of a much larger, more complex history. The Hubble tension is a conflict without villains, a mystery without a clear path to resolution. It is a clash between two truths, each supported by overwhelming evidence, yet fundamentally incompatible. And in that incompatibility lies the promise of discovery. For now, the universe keeps its secret. Two expansion rates exist where only one should. Two stories clash where one narrative was expected. And as this disagreement deepens, it becomes clear that whatever lies behind it has the potential to reshape our understanding of the cosmos in ways we cannot yet imagine. It begins with a quiet contradiction buried in the starlight of the oldest objects in the universe. These ancient stars, glowing faintly in the vast darkness of the cosmos, carry within them a secret that should not exist. According to the traditional timeline built around the Big Bang, the universe is approximately 13.8 billion years old. That number has been repeated in textbooks, documentaries, lectures, and scientific papers for decades. It was considered one of the most stable cornerstones of modern cosmology. But then astronomers began to study stars that seemed older, much older, than the universe that supposedly created them. Suddenly, the cosmic timeline no longer felt secure. These stars, particularly those found in the Milky Way's oldest clusters, behave like rebels defying the laws of cosmic chronology. Their composition, their luminosity, their evolutionary stage, all suggest that they are older than 13.8 billion years. Some estimates place their ages at 14 billion years, others at 14.5 billion, and a few even push closer to 15 billion. Even the lower end of these estimates should be impossible. A universe cannot contain objects older than itself. Yet here they are, shining like ancient witnesses to a history we thought we understood. Imagine standing at the entrance of a cathedral built long before recorded memory. Its stones seem too weathered, too ancient to match the era historians insist it belongs to. You glance at carvings that predate the supposed origin of the structure, inscriptions that whisper of events occurring before the cathedral should have existed at all. This is the sensation astronomers feel when confronting these stars. Their chemical signatures contain unusually low levels of heavy elements, indicating they formed when the universe was incredibly young. So young in fact that according to our standard timeline, they should not have had enough time to develop into what they are now. One of the most striking examples is the Methuselah star, officially known as HD 140283. 4 years, its calculated age exceeded that of the universe itself, forcing astronomers to revisit their methods again and again. Each recalculation pushed the number slightly downward, but the star stubbornly resisted fitting comfortably within the accepted cosmic timeline. Even at its most conservative estimate, it hovers dangerously close to being older than the Big Bang would allow. It stands as a quiet testament to the possibility that our timeline might be flawed or incomplete. These ancient stars are more than curiosities. They are cosmic anomalies that challenge the very structure of our understanding. According to the Big Bang model, the first stars should have formed several 100 million years after the initial explosion. Before that, the universe was too hot, too dense, too chaotic for star formation to occur. Yet some of these objects appear to have formed astonishingly early, almost immediately after the universe should have cooled enough to permit their creation. Their presence implies a universe that matured faster, cooled faster, or perhaps existed earlier than our models predict. This contradiction forces scientists to ask uncomfortable questions. Could the universe be older than we think? So, by how much? And what would that imply about the Big Bang? These inquiries open the door to possibilities that stretch beyond conventional cosmology. Perhaps the expansion rate has been miscalculated. Perhaps dark energy or dark matter behaves differently than expected, distorting our age estimates. Or perhaps the universe did not begin with a singular explosive event but transitioned from a prior state, giving it a hidden history older than its apparent beginning. The emotional weight of this possibility is profound. For generations, the Big Bang offered a sense of clarity, a clean moment when time began. But if stars older than the universe exist, then time may not be as linear, simple, or confined as we imagine. The universe may not have a single birth moment. It may have layers of creation, eras stacked upon eras, with each new cycle leaving behind relics from the one before. These ancient stars could be cosmic fossils from a previous epoch, surviving through transitions we cannot yet comprehend. As scientists examined these stars more closely, they found more anomalies that resist explanation. Their metallicity, an astronomical term referring to the presence of heavier elements, often contradicts expectations. Some stars appear too chemically primitive, as if they formed before the universe had produced enough heavy elements to seed them. Others appear too chemically advanced, suggesting they formed later in cosmic history. The inconsistency is striking. The stars do not fit a single timeline. They scatter across an age spectrum that challenges the tidy chronology cosmology once claimed to understand. The deeper we examine these contradictions, the more the universe begins to resemble an ancient manuscript filled with overwritten passages and hidden layers. Each star is like a word in a language we have only partially deciphered. Some phrases hint at a story older than the Big Bang, a story that precedes the explosion we have long considered the ultimate beginning. Like archaeologists discovering artifacts far older than the earliest known civilizations, astronomers now confront stars that seem to originate from a chapter of cosmic history we did not know existed. The tension grows stronger when paired with the discoveries of the James Webb Space Telescope. JWST has revealed galaxies forming incredibly early, far earlier than our models allow. Stars existed when they shouldn't. Structures appeared before they should. Everything seems to suggest a universe that moved faster, evolved quicker, and reached maturity long before the Big Bang timeline can accommodate. If galaxies and stars both appear older than expected, then the entire chronology of the universe may require a radical rewrite. Some scientists propose that the universe experienced a slow evolutionary phase before the Big Bang, a pre-expansion state in which time existed but matter had not yet arranged itself into familiar forms. Others suggest the Big Bang may not have been the true beginning but rather a transformation, a rebound, or a phase shift from a previous cosmic era. In such models, the universe could easily be older than 13.8 billion years. The Big Bang becomes less of a birth and more of a transition, one chapter in an ongoing cosmic book. There is awe in this possibility. Awe that the universe contains secrets so subtle and so ancient that even our most advanced instruments catch only whispers of their truth. Awe that the timeline of existence may stretch back further than our minds can fully grasp. Awe that the stars themselves preserve memories of eras beyond our current models. Memories etched in their light, their composition, their very being. Yet there is also fear. Fear that the foundations of cosmology, the age of the universe, the timeline of formation, the sequence of cosmic events, may be unraveling. Fear that our understanding of time itself may be incomplete. These ancient stars do not shout their defiance. They whisper it softly, persistently, through the quiet glow of their ancient light. And in those whispers lies a message. The story of the universe may be older, stranger, and far more complex than we ever imagined. In the earliest chapters of cosmic history, long before galaxies spiraled into elegant structures and stars ignited with nuclear fire, the universe should have been a chaotic fog. According to the Standard Model, matter at that time was scattered, disorganized, and far too turbulent to form anything resembling structure. It should have taken hundreds of millions of years for gravity to gather this primordial soup into the first proto-galaxies. But when astronomers peer back into the deepest reaches of space, into a past so ancient it stretches the limits of imagination, they find something that should not be there. They find structures that are too big, too bright, too complex, and far too early. These are the missing pieces of cosmic childhood, fragments of a story that refuse to fit the script we thought we understood. Imagine a world where ancient cities appear on Earth thousands of years before humans even evolved. Roads, temples, monuments, fully formed, impossible artifacts existing long before civilization should have been capable of building them. That is the sensation scientists feel when encountering early universe structures. Instead of simple, tiny clouds of gas barely beginning to condense, They find massive galaxies already swirling with unexpected organization. They find clusters forming faster than gravity should allow. They find objects that should not have had enough time to grow into what they are. It is as though the universe learned to build far earlier than the rules permit. One of the most startling revelations comes from the sheer mass of these early galaxies. According to theory, the first galaxies should have been small and dim, fragile flickers in a still-forming cosmos. But observations reveal galaxies boasting masses comparable to modern giants, structures packed with stars when the universe was only a few % of its current age. These cosmic behemoths should not exist so early. They challenge the timeline of growth that cosmologists spent decades constructing, suggesting that matter coalesced with astonishing speed, as if guided by forces or conditions we have not yet discovered. Even more perplexing is the level of order found in these structures. Spiral-like features, compact star clusters, and well-defined shapes appear long before turbulence should have settled. The young universe should have resembled a storm-tossed sea, chaotic and violent. Instead, in some regions, it looks almost serene, as though cosmic evolution proceeded with an efficiency that defies the expected rules of physics. This mismatch creates an intellectual tension that deepens with every new observation. Dark matter, the invisible scaffolding believed to shape the universe, is expected to play a key role in forming early structures. It should gather slowly, providing the gravitational wells that guide ordinary matter into forming galaxies. But the galaxies we observe appear to have formed too quickly for dark matter to assemble the necessary framework. It is as if the scaffolding was already in place, or formed in ways we do not understand. This discrepancy forces scientists to reconsider whether dark matter behaves the same way in the early universe as it does today, or whether it exists at all in the form we imagine. Even more mysterious are the early quasars, supermassive black holes shining with unimaginable intensity. These cosmic engines are powered by black holes with masses millions or billions of times greater than our Sun. Yet some of these quasars appear less than a billion years after the supposed beginning. According to calculations, there simply wasn't enough time for black holes of such size to form through ordinary processes. Their existence hints at accelerated growth or at a head start that defies the Big Bang timeline. They glow like cosmic lighthouses from a childhood universe that should have been far too young to host them. Then there are the enormous cosmic filaments, vast webs of matter that stretch across unimaginable distances. These structures should have taken billions of years to form, yet signs of their early development appear in epochs where the universe should still have been disorganized. The scale, precision, and early maturity of these filaments contradict the predictions of the Standard Model. They appear as ancient architectural lines drawn long before the cosmic blueprint should have existed. Each new discovery feels like a missing piece that refuses to lock into place. Instead of clarifying the picture, the pieces introduce more questions. How did such massive structures emerge so rapidly? Why do they appear in such advanced states? What force or mechanism accelerated their formation? These questions echo through research papers, conference halls, and late-night discussions among cosmologists struggling to reconcile theory with observation. The emotional impact is undeniable. Scientists who once believed they understood the broad strokes of cosmic evolution now face a universe that behaves like a prodigy, developing capabilities far earlier than expected. It is both thrilling and unsettling. The universe seems to be revealing a hidden layer of history, one that challenges the belief that the early cosmos was simple, slow, and straightforward. Some theorists propose that the universe may have been born with initial conditions far more structured than random quantum fluctuations suggest. Others argue that unknown forms of matter or energy may have shaped early growth. Still others propose that our understanding of gravity, especially at cosmic scales, may be incomplete. Modified gravity theories, exotic particle models, and even pre-Big Bang frameworks are considered in attempts to explain these anomalies. Yet none provide a definitive answer. The James Webb Space Telescope intensifies this mystery. Its powerful instruments pierce deeper into cosmic time, revealing galaxies that look too evolved, too bright, too massive. Each new image adds weight to the suspicion that the early universe was far more complex than the Standard Model allows. Instead of solving the puzzle, JWST widens it, revealing structures that appear not just early but impossibly early. The trouble is not that these objects exist, but that they appear everywhere we look. They are not rare exceptions, they are widespread. This suggests a systemic issue with our understanding of early cosmic evolution. The timeline may be misaligned. The processes may be incomplete. Or the Big Bang may not describe the beginning in the way we assume. As these anomalies accumulate, the story of cosmic childhood becomes more chaotic and more compelling. Instead of a slow, methodical emergence of structure, we see a universe that bursts into complexity with surprising speed. It challenges the narrative that the early universe was primitive and unformed. Instead, it hints at a cosmos with hidden maturity, one with a history that extends deeper than the timeline we currently accept. These missing pieces do not break the story of the Big Bang. They expand it, destabilize it, and demand that we search for the chapters we have not yet uncovered. They whisper of a universe that evolved faster, grew smarter, and revealed its structure sooner than our models predict. And in those whispers lies the possibility that the beginning of everything may not be as simple, as sudden, or as singular as we once believed. When the James Webb Space Telescope first unfolded its golden mirror in the vacuum of space, it felt like humanity was opening a new eye, one capable of looking deeper into the cosmic past than any instrument before it. Engineers celebrated its flawless deployment, astronomers whispered about the discoveries to come, and the world watched in awe as the telescope aimed its mirror toward the darkness. It was meant to confirm what we already believed about the universe's earliest years, to refine details of a story we assumed was largely correct. But instead it shattered that story. With every image it captured, JWST exposed cracks in the foundations of our understanding. It did not simply observe the universe. It broke it open. The telescope was designed to see the faintest glimmers of the earliest galaxies, those that should have been small, underdeveloped, and struggling to form in the young, chaotic cosmos. According to the Big Bang model, the early universe was still assembling itself in those first few 100 million years. Gravity had barely begun pulling gas into clumps. Stars had only just begun to ignite. Everything should have been primitive, dim, and infant-like. But when JWST revealed its first deep-field images, the galaxies staring back were anything but primitive. They were bright, massive, shockingly mature. Their structures were too organized. Their stellar populations too old. Their presence too numerous. And worst of all, they appeared at times when the universe should not have been capable of producing them. Imagine opening a history book expecting to see sketches of early human settlements, only to find photographs of bustling modern cities in the chapter marked Year Zero. Streets lined with skyscrapers. Populations already thriving. Systems already established. That is what astronomers experienced when JWST exposed galaxies that had matured far earlier than theory allowed. One of the most astonishing revelations was the sheer number of these early galaxies. Instead of a sparse scattering of tiny proto-galaxies, the telescope found a crowded landscape filled with objects that were too large and too bright. Some galaxies appeared to contain as much mass as the Milky Way, despite existing less than 500 million years after the supposed Big Bang. According to the standard cosmological timeline, there simply wasn't enough time for gravity to assemble such massive structures. Gas should not have cooled fast enough. Matter should not have clustered efficiently enough. The physics did not allow it. Yet there they were, fully formed where they should not be. Their existence struck the scientific community like a thunderclap. The colors captured by JWST, deep reds shifted beyond visible wavelengths, revealed not only the distance of these galaxies but also clues to their age. Many contained stars that appeared older than the universe should have permitted. Their chemical signatures hinted at multiple generations of stellar evolution. That means stars had already formed, exploded, and seeded their galaxies with heavier elements in a timeframe far too short to fit the traditional model. Instead of a universe in infancy, JWST revealed one that had somehow skipped ahead in its developmental timeline. The telescope also found unexpected shapes. Instead of chaotic blobs of matter, early galaxies displayed surprising organization. Disk-like formations, centralized bulges, and structural features that should have taken billions of years to sculpt. These galaxies behaved like seasoned dancers in a universe that should still have been learning its choreography. The impact was immediate. Papers flooded scientific journals. Conversations erupted in observatories and conferences. Some astronomers tried to reconcile the data with existing models, attempting to stretch the Big Bang timeline or adjust formation rates. Others argued that new physics might be required. Some even suggested that the foundational assumptions about cosmic beginnings might need revision. The quiet confidence that once surrounded early universe cosmology began to crumble. The deeper JWST looked, the worse the contradictions became. It detected enormous black holes, monsters millions or billions of times more massive than the Sun, lurking in eras where not even the first massive stars should have finished forming. These black holes were not struggling infants. They were titans actively consuming matter and blazing as quasars. For such enormous objects to exist so early, They would have needed either an impossible growth rate or a head start from something unknown, something beyond the Big Bang's straightforward timeline. And then there were the galaxies with extreme star formation rates, systems birthing stars at furious speeds that stretched or even violated theoretical limits. The universe at that age should not have possessed the conditions required for such explosive growth. Yet JWST found galaxy after galaxy lighting up the early cosmos with intense radiance, as though the universe were rushing into complexity instead of emerging slowly from simplicity. Even more troubling were the gravitational lensing observations, light from early galaxies bending around foreground objects in ways that suggested more mass existed in these early structures than models predicted. If these galaxies contained more dark matter than expected, that presented one contradiction. If they contained less, that presented another. Either interpretation strained the theoretical framework. The telescope also captured enormous cosmic filaments, vast web-like structures that stretch across unimaginable distances, far earlier than they should have formed. These filaments, which make up the cosmic skeleton of the universe, require vast timescales to grow. According to theory, they should not appear so clearly defined so soon. Yet JWST uncovered evidence of early large-scale structure that simply should not exist. Every image seemed to tell the same story: the early universe was too advanced, too organized, too fast-moving. It did not behave like a chaotic newborn struggling into existence. It behaved like a universe with a past, a universe that carried momentum or structure from an earlier era. Something was deeply wrong with the timeline we had constructed. Scientists faced a sobering realization: the most powerful telescope ever built had not confirmed the Big Bang model, it had exposed its weaknesses. It had illuminated inconsistencies hidden beneath decades of interpretation. It had ripped away the comfort of certainty, replacing it with a panoramic view of a cosmos far more mysterious than expected. Some researchers now propose that the early universe may have been denser or more efficient at forming stars than thought. Others suggest that dark matter may interact differently with ordinary matter in the early cosmos. A few entertain the possibility that the universe experienced a phase before the Big Bang, perhaps a contracting era, a bounce, or a more complex prehistory that seeded early structure. These ideas, once fringe, now enter serious discussion because the telescope leaves little room for the old narrative. There is awe in this upheaval, an emotional mix of fear, excitement, and wonder. The universe revealed by JWST feels alive, vibrant, rebellious. It pushes against the boundaries of our models. It defies the constraints of our equations. It forces us to confront the possibility that the cosmos is not a simple story beginning with a single explosion, but a vast, layered epic with chapters we have not yet discovered. JWST was built to show us the beginning. Instead, it may have revealed that the beginning we believed in was never the whole story. They appear in the darkness like forbidden clues in a mystery no one expected to encounter. Galaxies so old, so massive, and so bright that their existence seems to mock the timeline of the Big Bang. These early cosmic structures, revealed with stunning clarity by new telescopes, behave like ancient rebels defying the rules written for them. Instead of emerging slowly from a turbulent young universe, they stand fully formed at impossibly early moments, as if they came from a story preceding the one we've been told. Their presence is not subtle. It is loud, disobedient, and deeply unsettling. These early galaxies are called forbidden because, according to the standard cosmological model, they should not be able to exist. The universe at the time they formed was too young, too hot, and too chaotic to assemble coherent structures on such scale. It was supposed to be an age of cosmic fog, where gravity was only beginning its slow work of pulling matter into clumps. Yet instead of faint, shapeless patches of light, we find colossal galaxies glowing with surprising maturity. They contain more stars than models allow, arranged with a precision that should have taken billions of years to develop. Imagine someone discovering fully grown trees in a world only minutes old. Not seedlings. Not saplings. Entire trees towering over the landscape, with deep roots, thick trunks, and countless rings marking seasons that never should have happened. That is the shock astronomers feel when they observe these forbidden galaxies. Their brightness alone is a warning sign. Only massive, rapidly forming stars can produce such light. But those kinds of stars require dense clouds of gas, long timelines, and stable gravitational environments, conditions the early universe simply did not have. Even more troubling is their size. Some forbidden galaxies possess stellar masses rivaling large modern galaxies despite existing just a few 100 million years after the supposed beginning. The math does not add up. There was not enough time for matter to collapse, for stars to form and die, for multiple stellar generations to enrich the environment, or for galaxies to grow through mergers. If these galaxies are real, and the evidence leaves little room for doubt, then something is fundamentally missing from our understanding of how the universe evolved. The shapes of these galaxies deepen the mystery. Instead of chaotic, irregular blobs of material, many display ordered structures, disks, bulges, and spiral-like patterns. The young cosmos should have been too violent for such elegant organization. Collisions were frequent, gas pressures extreme, and gravitational interactions chaotic. Yet these early galaxies look strangely calm, as though they were sculpted by a process far faster and more efficient than any current theory describes. Chemical signatures provide another layer of contradiction. These galaxies contain heavy elements, carbon, oxygen, nitrogen, even iron, that require previous generations of stars to forge them. But there simply wasn't enough time between the Big Bang and the formation of these galaxies for multiple rounds of star birth and death. Heavy elements are cosmic fingerprints, telling us that these galaxies lived through lengthy cycles of violence and renewal. And yet they appear at a moment in cosmic history when even the first stars should have only just begun to ignite. Then there are the forbidden quasars, supermassive black holes that blaze with unimaginable intensity, found shockingly early in cosmic time. These black holes have masses millions or billions of times greater than the Sun. According to current theory, they should take billions of years to grow. Yet they appear less than a billion years after the supposed beginning. Their growth rate would need to be exponential beyond anything allowed by physics, or they would need to have formed from seeds far larger than any natural process predicts. Their existence, like that of the forbidden galaxies, defies all conventional expectations. Every attempt to explain these anomalies strains the limits of the standard model. Some propose that star formation in the early universe was far more efficient than predicted, but even extreme assumptions fall short of making these galaxies possible. Others propose that dark matter may have behaved differently, perhaps collapsing into structures faster than ordinary matter. But no version of dark matter physics currently explains the sheer mass and maturity of these early galaxies. Some suggest that black holes may have formed directly from collapsing gas clouds instead of from dying stars, giving them a head start. But that still does not explain the simultaneity of so many mature galaxies appearing so early. The forbidden galaxies do not merely challenge the timeline. They challenge the fundamental assumptions behind the timeline. If the early universe was capable of rapid, organized growth, then our understanding of its conditions, its density, temperature, evolution, may be significantly flawed. These galaxies hint at a universe that matured faster, evolved differently, or perhaps carried remnants from a previous cosmic state. A radical possibility emerges. The universe may have inherited structure from an earlier era. Perhaps a cycle of contraction and rebirth left behind patterns that shaped the newly expanding cosmos. Perhaps regions of the early universe were not uniform but carried imprints of conditions we have not yet imagined. Or perhaps the Big Bang was not a clean beginning, but a transition, a transformation of a universe already rich in structure. There is a haunting beauty in these possibilities. The forbidden galaxies act like ancient guardians of a truth we are not yet ready to understand. They glow not just with starlight, but with the weight of contradiction. Their very existence compels us to question the story we have built around the cosmos. They force us to imagine a universe older, deeper, and more complex than the one we thought we knew. And as telescopes continue to uncover more of these impossible structures, the message grows louder. The early universe was not the empty canvas of theory. It was already filled with breathtaking complexity, a mystery that refuses to be ignored. It lurks in the shadows of every galaxy, shaping the cosmos with an invisible hand. We cannot see it, cannot touch it, cannot capture it, yet its influence is undeniable. Dark matter has become one of the central pillars of modern cosmology, an unseen substance thought to make up most of the universe's mass. Without it, galaxies would tear themselves apart, stars would fly off into the void, and the cosmic web that stretches across billions of light-years would collapse into a shapeless fog. Dark matter is the ghost that organizes reality. But despite decades of searching, it remains exactly that, a ghost. And the longer we look for it without finding it, the more the entire cosmological model begins to tremble. The concept of dark matter emerged from a simple observation. Galaxies spin too fast for their visible mass to hold them together. In theory, the gravitational pull from stars, gas, and dust should keep them stable. But calculations showed that the outward centrifugal force was far stronger than the inward pull of gravity. The galaxies should have been flying apart. Yet they weren't. Something invisible had to be providing the extra gravitational glue. Something massive, silent, and unseen. Dark matter became the inevitable explanation, an invisible scaffold holding the universe together. But as astronomers studied galaxy rotation curves more closely, the mystery deepened. The missing mass was not random. It followed specific patterns, forming halos around galaxies and clusters, filling massive filaments that connected them, and shaping the universe's large-scale structure. Its distribution seemed too organized for something we couldn't detect. It behaved like a hidden architecture upon which the luminous universe was built. And that eerie order fueled the belief that dark matter must exist, even if it remained forever hidden from direct detection. Yet the search for dark matter has been a journey of repeated disappointment. Physicists built detectors deep underground, shielded by rock and earth, hoping to catch the faintest collision between dark matter particles and ordinary atoms. They built instruments in Antarctica, buried sensors in abandoned mines, and launched satellites into orbit, all designed to capture a single hint of contact. But the detectors remained silent. Year after year, experiment after experiment, nothing appeared. The ghost refused to show itself. This absence grows more troubling as the search becomes more sensitive. If dark matter existed in the form scientists expected, weakly interacting massive particles, then we should have detected them by now. The detectors are powerful enough. The technology is precise enough. And yet the silence continues. It is as if the universe is hiding something deliberately, or worse, as if we are searching for something that was never there. The contradictions surrounding dark matter extend far beyond failed detection. Some galaxies behave as though dark matter barely affects them at all, spinning in ways that contradict the expected gravitational contributions. Others seem to contain more dark matter than theory allows. A few galaxies appear to be missing dark matter entirely, defying the very framework built to explain their existence. These outliers crack open the possibility that dark matter may not be a single universal substance but part of a deeper, more complex phenomenon. Even more unsettling is the behavior of galaxy clusters. When astronomers observe collisions between clusters, they find that the visible matter sometimes separates from the gravitational effects attributed to dark matter. In some regions, the dark matter halo seems displaced. In others, it appears absent. These observations are so contradictory that even the most experienced cosmologists struggle to reconcile them with established theory. It is as if the invisible scaffolding became warped, broken, or rearranged in ways we cannot explain. The cosmic web, the vast interconnected pattern of filaments and voids spanning the universe, is also dependent on the existence of dark matter. Simulations of cosmic evolution require enormous amounts of dark matter to shape the web into its recognizable form. Yet JWST observations reveal massive early structures that should not have had enough time for dark matter to cluster into the necessary patterns. The scaffolding appears to have formed too quickly, as though the universe already had structure built into it from the very beginning. This implication is profound. It suggests that dark matter may not be forming structures, it may be inheriting them. These contradictions push some scientists toward alternative explanations. One possibility is that dark matter is not a particle but a field, something that permeates all of spacetime like a cosmic fluid. Another possibility is that dark matter interacts with itself or with gravity in ways we have not yet conceived. And then there is the boldest idea of all, that dark matter does not exist. Instead, gravity itself may behave differently on cosmic scales. Modified gravity theories attempt to explain galaxy rotation without invoking invisible mass. These theories propose that at enormous distances or extremely weak accelerations, gravity changes its behavior. Rather than requiring additional mass, the laws of motion warp themselves to fit the observed data. Such models can mimic the effects of dark matter in some cases but fail in others. They solve some puzzles while creating new ones. The universe refuses to conform to a single clean explanation. As each new observation emerges, the emotional tension grows. Dark matter was supposed to be the quiet foundation of the cosmos, the invisible hero that holds everything together. Instead, it has become a source of uncertainty, a shadow that refuses to reveal its form. The more we learn, the more contradictory it becomes. It acts massive but remains undetectable. It shapes galaxies but behaves inconsistently. It explains the cosmic web but appears too early. It fits the data until the data grows more detailed, and then it falls apart. Cosmologists now stand at a crossroads. If dark matter exists, it must be stranger than any particle we have ever discovered. Something beyond the standard model of physics, something that interacts with the universe in a hidden, unpredictable way. If dark matter does not exist, then our understanding of gravity, spacetime, and cosmic evolution may require a complete overhaul. Either option points toward a universe far more mysterious than we imagined. There is a haunting beauty in this uncertainty. The ghost we chase may be the key to understanding everything. Or it may be the sign that we have misunderstood the cosmos for decades. Dark matter stands at the center of the largest existential question in modern cosmology, a question that grows more urgent with every contradiction unveiled. And as telescopes probe deeper and detectors grow more sensitive, the universe seems to whisper a challenge: find the truth hidden in the darkness, or admit that we have been illuminating the wrong shadows all along. It is the quietest force in the universe, yet it commands the largest structures in existence. It cannot be seen, touched, or measured directly, but its influence stretches across billions of light years. It pulls nothing closer. It pushes everything apart. It behaves like a cosmic puppeteer, manipulating the expansion of spacetime with a subtlety so vast that only the largest scales reveal its presence. This force, dark energy, has become one of the most haunting mysteries in modern physics. It is the silent ruler of the cosmos, yet we do not know what it is, where it came from, or why it behaves the way it does. Dark energy first entered the scientific story not as a predicted phenomenon but as an unwelcome surprise. Astronomers studying distant supernovae expected to find evidence that the expansion of the universe was slowing down. After all, gravity should gradually pull matter together, reducing the rate of cosmic growth over time. Instead, they found the opposite. The expansion was speeding up, accelerating as though pushed from within by an invisible force. This revelation stunned the scientific community. Something was overpowering gravity on the grandest scales imaginable. Something was rewriting the cosmic script. The term dark energy was coined to describe the unknown cause of this acceleration, but the name is little more than a placeholder. It conveys ignorance more than understanding. We call it energy because it acts like energy in Einstein's equations. We call it dark because we do not know what it is. It remains a riddle wrapped inside equations that barely contain it. Yet despite our ignorance, dark energy dominates the universe, making up nearly 70% of everything that exists. It is the majority owner of reality and we do not know its face. Imagine standing on a vast, empty plain, feeling a wind you cannot see. It pushes against you, reshaping the landscape around you, but no matter how you search the horizon, you find no source for the breeze. This is the experience scientists face when trying to understand dark energy. They observe its influence everywhere: galaxies drifting apart faster, distances growing wider, the fabric of space stretching like an ever-expanding canvas, but they find no trace of the force causing it. The universe behaves as if filled with an invisible pressure that increases its size over time. The mathematics describing this phenomenon are elegant but deeply unsettling. According to general relativity, energy affects the curvature of spacetime. Dark energy behaves like a form of negative pressure, causing spacetime itself to expand. But this description raises more questions than it answers. What kind of energy has negative pressure? Why does it permeate all of space equally? Why did it become dominant only recently in cosmic history, rather than from the very beginning? These questions form cracks in the theoretical foundation, cracks that widen with each new observation. Even more puzzling is the apparent constancy of dark energy. Measurements show that its density remains the same over time, even as the universe expands. Ordinary matter becomes diluted. Radiation spreads thinner. But dark energy does not weaken. As space grows, dark energy seems to grow with it, filling every new volume of space instantly and uniformly. This behavior defies all known physics. It suggests that dark energy is not simply a substance but a property of spacetime itself, a feature baked into the universe's very fabric. This leads to one of the most disturbing possibilities in cosmology. The universe may not only be expanding but accelerating in a way that has no natural endpoint. If dark energy remains constant or increases over time, it could eventually tear apart galaxies, solar systems, planets, atoms, and even spacetime itself. Scientists call this hypothetical future the Big Rip, a scenario in which the universe ends not with a collapse but with a shredding. It is a chilling reminder of how little control we have over the cosmic forces that shape our existence. Yet the mystery deepens further when we consider the early universe. According to inflation theory, the cosmos experienced a burst of unbelievably rapid expansion in the first fraction of a second after the Big Bang. This inflationary phase behaves eerily like the effects of dark energy, an exponential stretching driven by a mysterious field. But inflation happened long ago and then ceased, while dark energy works slowly and steadily in the present. Are the two connected? Are they separate phenomena? Or is dark energy simply inflation reawakening on a different scale? These questions blur the boundaries of cosmology and push us toward the edges of theoretical physics. Dark energy also complicates observations of galaxies and galaxy clusters. When scientists attempt to map the universe based on gravitational behavior, they find inconsistencies that suggest dark energy may not be uniform after all. Some regions appear to feel its influence more strongly or more weakly. Others seem to resist its effects. These variations challenge the assumption that dark energy is constant and raise the possibility that it may evolve, fluctuate, or interact with matter in ways we have not yet imagined. Alternative theories attempt to explain dark energy without invoking unknown substances. Some propose modifications to gravity, suggesting that Einstein's equations break down at cosmic scales. Others propose that spacetime contains hidden dimensions that subtly distort our observations. A few radical theories suggest that what we interpret as acceleration may be an illusion created by inhomogeneities in the universe's structure. But each alternative faces its own set of contradictions, dead ends, and paradoxes. None solve the puzzle cleanly. The emotional weight of dark energy is immense. It forces us to confront the possibility that the universe is governed by a force that lies completely outside our understanding. It forces us to admit that the majority of reality is not made of stars, planets, or even dark matter, but something deeper, stranger, and more elusive. The cosmos is driven by a pressure that does not behave like any force we know, and its ultimate purpose or origin is hidden behind a veil we cannot yet pierce. Dark energy is both the universe's most silent whisper and its loudest warning. It stretches reality without a sound. It accelerates expansion without effort. It shapes the destiny of everything that exists while remaining beyond the reach of our instruments. And as we search for its nature, the universe seems to watch patiently, offering clues wrapped in contradictions. One day we may uncover the truth. Or the truth may remain out of reach, forever dancing just beyond the limits of observation. But for now, dark energy remains what it has always been, the silent puppeteer behind the cosmic stage, pulling the strings of existence while revealing nothing of itself. Inflation was once considered the most elegant fix in the history of cosmology, an idea so simple, so powerful, and so perfectly timed that it swept through scientific circles like a revelation. According to the theory, the universe underwent a brief period of unimaginably rapid expansion in the first tiny fraction of a second after the Big Bang. Space itself ballooned faster than the speed of light, ironing out irregularities, smoothing the cosmic fabric, and setting the stage for everything that followed. Inflation explained the uniformity of the cosmic microwave background. It explained why distant regions of space looked so similar despite being too far apart to have exchanged information. It explained the large-scale structure of the universe. For decades, inflation was hailed as a triumph, a miracle solution that solved multiple cosmic puzzles at once. But as the data grew more precise, the miracle began to crack. Inflation was no longer a flawless hero, it became a suspect under interrogation. The equations that once seemed elegant revealed complications. Predictions that once matched observations began to drift. The deeper scientists looked, the more inflation started to resemble a beautiful story built on assumptions that were never fully tested. The hero of cosmology found itself on trial. One of the deepest concerns arises from inflation's reliance on an unknown field, an exotic energy that appeared from nowhere, triggered rapid expansion, and then vanished without a trace. This inflating field has never been detected. No particle, no interaction, no remnant of it has ever been found. Inflation theory asks us to believe in a force that turned the universe inside out in a blink and then simply disappeared. It is a narrative device so convenient that many physicists began to question whether inflation was a true physical event or simply a mathematical patch applied to a broken model. When we simulate inflation, we find that it works only if the inflating field is tuned with extraordinary precision. If its strength is even slightly off, inflation either does not start or does not stop. The universe becomes empty or collapses instantly. The required fine-tuning is so delicate that it borders on impossible. It is like asking a cosmic architect to balance a pencil on the tip of a needle in the middle of a storm. The theory works, but only under conditions that seem implausibly perfect. Even more troubling are the predictions inflation makes about the cosmic microwave background. Inflation suggests that tiny quantum fluctuations should be frozen into the early universe as specific patterns, ripples in density that later became galaxies and clusters. But when scientists measured these patterns with increasing precision, some features failed to align with the inflationary predictions. Certain large-scale anomalies, directional asymmetries, and unexpected cold spots refused to fit the inflation model cleanly. These inconsistencies hinted that inflation, while powerful, may not be the full story. The deeper problem is philosophical. Inflation was supposed to be a simple explanation, but over time it evolved into a sprawling set of models, each with different initial conditions, parameters, and assumptions. Instead of a single theory, inflation became a landscape of countless versions. The more flexible it became, the easier it was to fit any data, and the less predictive power it held. A theory that can explain anything ultimately explains nothing. The elegance that once defined inflation was fading. Then came the most dramatic twist. Inflation predicts that inflation never fully ends. According to many versions, while our region of the universe finished inflating, other regions continue expanding endlessly. This leads to a bizarre consequence. An infinite multiverse composed of countless bubble universes, each with different physical laws, different particle types, and different cosmic histories. Inflation does not merely expand space, it expands possibility itself. While intriguing, this prediction pushes the theory into territory that is impossible to test. It transforms cosmology from a science grounded in observation into one that wanders into philosophical speculation. Critics argue that if inflation naturally leads to infinite universes, then it cannot be falsified. There is no way to observe these hypothetical universes, no way to measure their properties, no way to confirm or deny their existence. This places inflation precariously close to unfalsifiable metaphysics rather than empirical science. Some physicists openly call inflation post-empirical, meaning it cannot be tested through experiments. The moment a theory becomes immune to contradiction, it loses its scientific foundation. For many cosmologists, this is the moment inflation began to collapse under its own weight. New observations add further pressure. JWST has revealed early galaxies and structures forming far more quickly than inflation-based models predict. The universe appears too organized, too massive, too early. Inflation assumes an initial smoothness, but JWST suggests complexity emerging almost instantly. Inflation can be modified to accommodate this, but every modification widens the gap between theory and evidence. It becomes a shifting target, adapting endlessly without offering concrete predictions. The cosmic microwave background exposes another wound in the theory. Inflation predicts a specific type of gravitational wave imprint, a curling polarization pattern known as B-modes. Scientists launched experiments across Antarctica and high-altitude observatories hoping to find these primordial signatures. If detected, they would be the smoking gun of inflation. But despite decades of attempts, the signal remains absent. The universe is silent where inflation demands it should echo. Some hope remains that future telescopes may still discover these primordial gravitational waves. But the longer the silence continues, the heavier the doubt becomes. If inflation produced no detectable waves, then either it happened under extremely unusual conditions or it did not happen at all. Both possibilities shake the foundations of the standard cosmological model. The emotional reaction within the scientific community is complex. Some cling to inflation because it remains the best-known explanation, even with its flaws. Others search for alternatives, new theories that avoid inflation's fine-tuning, its undetectable fields, and its infinite universes. Ideas like bouncing cosmologies, emergent models, cyclic universes, and quantum gravity approaches attempt to rebuild the early universe from scratch. These theories propose that the Big Bang was not a beginning but a transition, a transformation of something older. Unlike inflation, they do not require perfect tuning or exotic fields that vanish without trace. Inflation was designed to answer mysteries. Now it creates them. It was meant to simplify cosmology. Now it complicates it. It was once a triumphant cornerstone of the Big Bang narrative. Now it stands as a symbol of uncertainty, a theory balanced delicately on assumptions that crumble under scrutiny. This does not mean inflation is wrong, but it may be incomplete, misunderstood, or merely one part of a much larger and more intricate cosmic story. It may be the shadow of a deeper process or the echo of a hidden era whose true nature we have yet to uncover. And as inflation stands on trial, the universe seems to whisper once more. The truth of the beginning is stranger, more layered, and more elusive than the elegant theories we crafted to explain it. The multiverse began as a speculative whisper, a side effect of equations, a distant consequence of inflation theory, a mathematical shadow that most physicists never expected to take seriously. But over time that whisper grew louder. Inflation, with all its complications and contradictions, seemed to point toward a reality far stranger than the one we inhabit. Instead of one universe, it suggested countless universes, each bubbling into existence with its own rules, its own constants, its own cosmic history. What began as a theoretical afterthought became a dizzying possibility, our universe may be just one chamber in an infinite cosmic labyrinth. The idea is both intoxicating and unsettling. On one hand, it offers an escape hatch from the mounting contradictions in cosmology. If our universe seems too finely tuned for life, too balanced to be random, or too structured too early, then perhaps that is because we are living in one universe out of countless possibilities. In the multiverse, every configuration happens somewhere. If one universe collapses under its own contradictions, another universe succeeds with different values. The unlikely becomes inevitable. The impossible becomes ordinary. Our existence becomes not a miracle but a statistical inevitability. Yet the multiverse also feels like a philosophical abyss. If there are infinite universes, then our reality loses its uniqueness. Everything that can happen does happen somewhere. Every life has infinite variations. Every decision branches into countless outcomes. The multiverse transforms the cosmos from a singular story into an endless library of fractured narratives. Some find comfort in this vastness, others feel swallowed by it. The emotional weight of the idea stretches far beyond equations. The scientific argument for the multiverse rests heavily on inflation. According to many models, inflation never ends everywhere at once. While it stops in some regions, allowing galaxies, stars, and life to form, it continues elsewhere, forever expanding, creating bubbles of space that pinch off into their own universes. Each bubble cools and evolves independently. Some may be empty. Some may be chaotic. Some may be governed by physics utterly alien to our own. Our universe could be just one bubble in an infinite cosmic foam. But this explanation, elegant as it may seem, hides a troubling truth. The multiverse cannot be observed directly. We cannot see beyond the boundaries of our cosmic horizon. We cannot detect other universes, measure their properties, or test their predictions. The multiverse explains everything and nothing at once. It provides answers without offering evidence. It satisfies mathematical models while escaping the reach of scientific verification. For many physicists, this is deeply unsettling. A universe we cannot observe may be mathematically appealing, but it risks stepping outside the realm of science altogether. Still, the multiverse refuses to disappear. It reappears in string theory, where different ways of compactifying dimensions lead to a nearly infinite landscape of possible universes. It reappears in quantum mechanics, where every quantum decision may split reality into new branches. It reappears in black hole physics, where some theories propose that each black hole could give birth to a new universe on the other side of its singularity. Everywhere scientists turn, the idea of multiple universes creeps back into the conversation like a quiet inevitability. And yet, the multiverse introduces new mysteries instead of solving old ones. If infinite universes exist, why does ours look the way it does? Why does it contain galaxies arranged in immense filaments, stars forming in elegant patterns, and laws of physics so precisely tuned that life can emerge? The multiverse says this is simply luck. A cosmic lottery we happen to win. But such an explanation feels hollow to many. It replaces understanding with convenience, replacing physical law with randomness on a scale beyond imagination. Some argue that the multiverse is a distraction, a theoretical escape route invented to protect cosmological models that cannot be reconciled with observations. If inflation predicts structures that should not exist, then the multiverse provides an easy out. These contradictions must be the result of our universe being one of many. If dark energy behaves inexplicably, then perhaps we simply inhabit a universe where dark energy takes on a particular value. Instead of revising the foundations of cosmology, the multiverse allows them to remain untouched. Others argue the opposite, that the multiverse is not an escape but a deeper truth, that our discomfort reveals the limits of human intuition rather than flaws in the theory. They suggest that just as Earth once seemed the center of the cosmos because it was familiar, our universe seems unique only because we cannot see beyond its borders. The multiverse forces us to confront a larger, more complex reality, one where our cosmic home is ordinary, not exceptional. The emotional landscape of the multiverse is filled with contradictions. It offers liberation from fine-tuning while evoking existential vertigo. It expands the boundaries of reality while dissolving the significance of our own. It solves mathematical problems while raising philosophical ones. It feels at once inevitable and impossible, scientific and speculative, profound and unsettling. Yet the most compelling reason to consider the multiverse may lie in the mounting problems with the Big Bang model itself. If early galaxies formed too quickly, if stars are older than the universe should allow, if dark matter remains undetected, if dark energy behaves inexplicably, and if inflation collapses under scrutiny, then perhaps our universe does not make sense alone. Perhaps its inconsistencies arise because we are viewing only one slice of a much larger cosmic structure. The forbidden galaxies, the unexpected structures, the impossible timelines, they may not be errors but windows into a deeper reality. They may hint that our universe is not isolated but connected, however loosely, to a wider space of possibilities. The multiverse is not comforting. It is not simple. It is not tidy. But it may be the doorway through which the next revolution in cosmology emerges. It may be the lens that reveals the true scale of existence, and the true limits of our understanding. And as we stand at the edge of this dizzying possibility, one truth remains clear. If the universe is part of a multiverse, then the mystery of everything is far deeper than we ever imagined. The idea that the universe could die and be reborn is as old as human imagination itself. Ancient myths spoke of worlds ending in fire, collapsing into darkness, and rising again from cosmic ashes. For most of scientific history, these ideas were dismissed as poetic metaphors, beautiful but not grounded in physics. Yet as the cracks in the Big Bang model widen, these old stories begin to feel strangely relevant. Modern cosmology now entertains a possibility once thought unscientific, that the universe may not have a single beginning but a cycle of beginnings. A cosmos that contracts, collapses, rebounds, and expands again in an endless loop of destruction and renewal. This concept reshapes everything we thought we knew. Instead of a universe born from a singular explosion, the cosmos becomes a phoenix, rising again and again from the remnants of its previous self. Each cycle leaves behind faint imprints, subtle fingerprints embedded in the structure of reality. These imprints may be hiding in the cosmic microwave background, in the distribution of galaxies, or even in the forbidden structures that appear too early in the universe's timeline. If the universe has lived many lives, then what we call the Big Bang might be nothing more than the latest reset. One of the strongest motivations for cyclic models comes from the near-perfect smoothness of the cosmic microwave background. Inflation was originally invented to explain this smoothness, but its flaws and fine-tuning issues make it an increasingly fragile solution. Cyclic theories offer an alternative. Perhaps the smoothness was inherited from a previous cosmic era. If the universe once collapsed toward a state of extreme density and uniformity before rebounding, then the initial conditions for the next expansion would naturally be smooth without the need for an exotic inflation field. In this way, cyclic models solve problems that inflation struggles with, not by introducing new forces, but by expanding the history of the universe itself. Imagine a cosmic heartbeat. A universe expands for billions of years, forming galaxies, stars, and life. Eventually, dark energy could slow or reverse, causing everything to fall back inward. Structures collapse. Stars burn out. Space contracts into a blazing, dense state. And then, at the moment of maximum pressure, the universe rebounds, releasing a new wave of expansion. In some models this bounce is smooth. In others it is violent. But in all versions the cosmos does not end, it transforms. One version of the cyclic universe, known as the ekpyrotic model, suggests that our universe's Big Bang was triggered not by a singular explosion but by a collision between higher-dimensional branes. In this framework, our universe is a three-dimensional surface floating in a higher-dimensional space. When two such surfaces collide, they release immense energy, creating what appears to us as a Big Bang. After the collision, the branes move apart, the universe expands, and eventually they approach each other again, triggering another cycle. This model explains smoothness, flatness, and structure without requiring inflation, offering a radically different view of cosmic origins. Another model, based on loop quantum cosmology, suggests that the universe's collapse halts at a minimum size because of quantum effects. Instead of reaching an infinite singularity, spacetime becomes discrete at the smallest scales, creating a quantum bounce that reverses contraction. This scenario implies that the Big Bang was actually the Big Bounce, a transition from a previous collapsing universe to our current expanding one. If true, then the universe has no beginning in the traditional sense. It stretches infinitely backward through cycles of contraction and expansion. These theories bring with them profound implications. If the universe is cyclic, then time itself becomes a circle rather than a line. The beginning is no longer a fundamental concept. Every origin is also an ending. Every ending becomes a beginning. The emotional impact of this idea is immense. It transforms the cosmos from a fleeting event into an eternal process. It suggests that existence is part of a grand rhythm beyond human comprehension. Death becomes transformation, not termination. But cyclic models also raise unsettling questions. If the universe has undergone countless cycles, what remains from previous eras? Are there ancient signatures buried deep in the cosmic background radiation? Are the early, impossible galaxies remnants of structures formed before the last bounce? Could black holes be portals through which old universes leave their mark on new ones? Some theories even suggest that information from previous cycles could survive through subtle quantum imprints, meaning the universe itself carries memories across cosmic ages. These possibilities ignite both excitement and dread. If the universe has existed through infinite cycles, then our understanding of time, causality, and existence must be rewritten. The Big Bang ceases to be a creation event and becomes a transition. The laws of physics may not be fixed but may evolve from cycle to cycle. Some cycles could last longer than others. Some could produce universes rich with structure and life. Others could be barren and chaotic. We might be living in a particularly stable or fortunate cycle, one among countless variations. Yet the cyclic idea solves one of the most troubling problems in cosmology: why the universe seems fine-tuned for life. In an endless sequence of cycles, it is statistically inevitable that some universes will have conditions favorable to complexity. This does not require a multiverse with branching universes. It requires only one universe living many lives. And in one of those lives, conditions align just right for galaxies, stars, and conscious beings to emerge. The evidence is still indirect, but hints accumulate. Certain anomalies in the cosmic microwave background, cold spots, directional patterns, and unexpected correlations, have been interpreted as potential relics from before the Big Bang. Unusual alignments in the distribution of galaxies may point to structures older than the expansion that supposedly created them. While none of these observations prove a cyclic universe, they deepen the suspicion that our cosmic history may be far longer and more layered than we imagine. The emotional resonance of this concept is powerful. If the universe is cyclic, then nothing truly ends. Stars die but new stars form. Galaxies merge and collapse but new galaxies emerge. Even the universe itself dissolves only to be reborn. This vision is both beautiful and humbling. It places humanity within a cosmic ecosystem of eternal renewal, where existence is woven into an infinite tapestry of cycles. Yet this same beauty carries a haunting undertone. A cyclic universe suggests that our current cosmic age is temporary. Eventually, everything we know, every star, every planet, every atom, will be drawn back into contraction. The night sky will dim. Galaxies will drift together. Space will compress. And the universe will prepare for another beginning. In the end, cyclic cosmology offers a vision of reality that is both ancient and revolutionary. It bridges myth and science. It merges destruction and creation. It transforms the universe from a single story into an endless epic. And in that epic, the Big Bang is not the beginning, it is merely one heartbeat in an eternal cosmic rhythm. Quantum mechanics is the realm where intuition collapses, where logic dissolves, and where reality behaves like a riddle wrapped in a dream. When cosmologists attempt to push beyond the Big Bang, beyond time, beyond classical physics, they inevitably enter this strange domain. Here, particles flicker between states, probability replaces certainty, and events refuse to follow the clean, linear causality that governs ordinary life. To understand the earliest moments of the universe, scientists must confront a truth that feels almost hallucinatory. The universe began in a place where the rules we rely on no longer apply. The story of creation slips into quantum territory, and the familiar dissolves instantly. Imagine a stage painted in shifting colors, where actors appear and disappear before your eyes, where movements obey patterns you cannot predict. This is the quantum landscape. In this realm, particles do not have definite positions or velocities. Instead, they exist in clouds of possibility, waiting for observation to force them into form. Time does not flow smoothly. It stutters, hesitates, and intertwines with space in ways that shatter everyday comprehension. And in the earliest moments of the universe, before atoms, before forces, before spacetime itself, this was the only kind of reality that existed. Classical physics breaks down long before we reach the Big Bang. When space is compressed to unimaginable densities, when the entire universe is compacted into a region smaller than an atom, Einstein's equations simply stop working. They produce infinities, mathematical explosions that signal the failure of the model. To go earlier, to go deeper, we need quantum rules. And quantum rules do not offer the comfort of clear beginnings. They offer a blur, a haze, a shimmering landscape where existence is neither one thing nor another. One interpretation proposes that the universe did not emerge from a singular point but from a quantum fluctuation, a temporary disturbance in a timeless quantum field. In this view, the universe blinked into existence like a spark in a void, not because of a physical cause but because quantum laws allow temporary creations. But this idea, while imaginative, raises haunting questions. If the universe emerged from a fluctuation, what was fluctuating? What existed before time began? How can a fluctuation occur without a backdrop of space or time? These questions ripple like echoes through the quantum fog, refusing to settle. Another approach suggests that the early universe was governed by a wave function, a mathematical description of all possible states existing simultaneously. In this scenario, the universe did not choose a single path at its origin. Instead, it existed as a superposition of countless possible beginnings. Only later, as the cosmos expanded and cooled, did one version of reality crystallize into the universe we now observe. This interpretation transforms the origin of everything into a vast quantum canvas, where multiple histories overlap and interfere like waves on a shore. Quantum cosmology becomes even more unsettling when we explore the idea that time itself is not fundamental. In some models, time emerges gradually from underlying quantum processes, like a pattern rising from chaos. Before that emergence, the universe existed in a timeless state, not frozen, not moving, but utterly beyond our conceptual grasp. Asking what happened before time began becomes meaningless, like asking what lies north of the North Pole. The mind reaches for understanding and grasps only air. One of the most provocative quantum ideas is that the universe may have come into existence through tunneling, a process where particles cross barriers they should not be able to cross. In quantum mechanics, impossibility becomes probability. Perhaps the universe tunneled from a prior state, slipping through the barriers of non-existence into existence. This concept is breathtaking but deeply disorienting. It suggests that reality itself emerged through a kind of cosmic escape act, violating classical impossibility in a way only the quantum realm allows. Quantum gravity theories attempt to merge Einstein's geometry with quantum rules. Some propose that spacetime is not continuous but made of discrete units, tiny quanta of space and time woven together like pixels in a cosmic screen. If so, the Big Bang was not an infinite explosion but a transition between different configurations of this quantum fabric. Others suggest that at the smallest scales, spacetime behaves like foam, a restless, bubbling sea of quantum fluctuations constantly forming and dissolving microscopic wormholes, loops, and topological twists. In such a universe, the beginning may not be a smooth moment but a chaotic dance of quantum geometry. These ideas carry emotional weight because they dismantle our sense of reality. In the quantum domain, identity blurs. Origins blur. Even causality blurs. The comforting image of a universe beginning with a single explosive moment dissolves into a shimmering sea of probability. The universe becomes less like a story with a clear starting point and more like a dream crystallizing out of quantum haze. Quantum beginnings also raise the possibility that the universe did not begin at all, not in the traditional sense. It may have existed eternally as a quantum state, oscillating through probabilities until conditions allowed a classical universe like ours to emerge. In this view, the Big Bang was not a moment of creation but a moment of transition, the point at which the universe shifted from quantum ambiguity to classical clarity. Before that transition, reality may have had no form at all. This perspective introduces a kind of cosmic déjà vu. If the universe exists eternally in quantum form, then every moment of existence, including the emergence of galaxies, stars, life, and consciousness, is woven into a deeper, timeless reality. It suggests that the quantum universe, though incomprehensible, holds within it all possible histories, all possible futures, all possible universes. The Big Bang becomes merely one crystallized thread in an infinite tapestry. Quantum cosmology does not offer easy answers. It does not provide a clean narrative or a simple beginning. Instead, it confronts us with a universe born from uncertainty, shaped by probability and governed by rules that bend logic. It reminds us that reality at its deepest level is stranger than any story we have ever told. And as we push closer to the truth, the quantum frontier stands before us, enigmatic, shimmering, and waiting to reveal the secrets of a beginning that may never have been a beginning at all. The idea that the universe might have no beginning is one of the most disorienting concepts in modern cosmology. For generations, the Big Bang has served as a comforting anchor, our cosmic day one, the moment when existence sparked into motion. A beginning implies a story, a direction, a point from which everything unfolds. But what if that anchor was never real? What if time stretches backward not for billions of years but infinitely, without origin, without a first moment, without a boundary where existence suddenly switched on? In this view, the universe is not a firework exploding into being. It is an endless horizon, a cosmic plane with no starting line, and its vastness becomes even harder to comprehend. Imagine standing on an infinite desert. No matter which direction you walk, you never reach an edge. The landscape stretches on forever, indifferent to your presence, offering no clues about where it began because it never did. In an emergent universe, time itself behaves like this endless desert. Instead of springing forth from a singular explosion, time gradually emerges from underlying physical processes. It thickens, crystallizes, takes shape, like ice forming on a pond. Before the freeze, there is no rigid structure, no clear sequence. But something exists, something deep and formless, a state where potential precedes order. This concept erases the need for a creation event. In emergent models, the universe always existed in some form, perhaps as a timeless quantum state, perhaps as a stable energy sea, perhaps as a primordial equilibrium that had no motion, no direction, no entropy. Then, slowly and naturally, the conditions shifted. Complexity arose. Time gained a direction. The universe entered a phase where patterns could develop, where particles could appear, where expansion could unfold. What we call the Big Bang is not the beginning, it is a transition, a threshold between a timeless cosmos and a temporal one. One of the most compelling motivations for these models is a deep contradiction at the heart of the Big Bang. Singularities do not make physical sense. A singularity is a point where equations produce infinities and logic breaks down. It is a mathematical red flag, the universe shouting that the model cannot be trusted there. Instead of accepting a singularity as a beginning, emergent theories treat it as a signpost pointing toward a deeper layer of physics. Just as the idea of absolute zero once hid the quantum world beneath it, the Big Bang singularity may hide a timeless reality we are only beginning to imagine. In some emergent universe models, the cosmos begins in a steady, static state, full of energy but not in motion. It is a cosmic lake, perfectly calm with no ripples of time or space. Over unimaginable stretches of existence, tiny fluctuations accumulate. Eventually, one of these fluctuations becomes unstable, triggering expansion. But there was no singular moment of creation. The lake did not appear from nothing. It simply shifted from stillness to motion. Its calm surface broke and the ripples became time. Other models suggest that the universe existed in a quantum gravitational state where spacetime itself had not yet formed. Instead of a fabric woven with dimensions, reality consisted of quantum relations, nodes of information interacting without geometry. As interactions intensified, spacetime emerged like a woven tapestry forming from threads. Time became a property of the relationships between these nodes, not an external backdrop. In this view, the universe before the Big Bang was not a place, it was a condition. This leads to a profound realization. Time may not be fundamental. It may be emergent, like temperature or pressure, arising only when enough complexity exists. Before that complexity, asking what happened earlier becomes meaningless. Not because nothing existed, but because earlier did not yet exist as a concept. The emotional weight of this idea is immense. A universe without a beginning feels unsettling because humans long for origins. We crave a first moment, a spark, a reason. But cosmology increasingly suggests that nature does not share our desire for a beginning. The cosmos may not need a birth story. It may simply be. These models also help address several major problems that plague the Big Bang framework. The horizon problem, why regions of the early universe appear uniform despite being too far apart to have interacted, is elegantly resolved in emergent theories. If the universe existed in a timeless equilibrium before expansion, then every region had infinite time to balance itself. Uniformity was not achieved suddenly, it was simply inherited. The flatness problem, the fact that the universe's geometry is astonishingly close to perfectly flat, also becomes easier to understand. A static or slowly evolving eternal universe can naturally settle into a stable configuration long before expansion begins. No delicate fine-tuning is required. Flatness becomes an outcome, not a coincidence. Even the mystery of early structures, the galaxies and black holes that appear too quickly, looks different in an emergent model. If time effectively stretches back infinitely, then the period before expansion could have set the stage for accelerated formation. The universe might have had far more preparation time than the Big Bang narrative allows. These ideas are compelling, yet they raise unsettling philosophical questions. If the universe had no beginning, does it also have no ultimate cause? If time is emergent, what does it mean for our understanding of causality, meaning, and existence itself? If the cosmos is eternal, then the story of reality has no opening chapter, only an endless middle. The human mind strains against this. Our narratives depend on beginnings. We define identity through origin stories. A universe without one challenges not only our physics but our psychology. Yet the astronomy of the last decade offers hints that the universe may indeed be older, or more eternal, than we thought. The ancient stars that appear older than the universe, the structures that formed too early, the galaxies that matured too fast, all whisper the same unsettling possibility. The timeline we use is wrong because the beginning we assume never existed. In an emergent universe, there is no need for a magical instant where everything appears from nothing. No arbitrary law that time suddenly ignites. No metaphysical leap from non-existence to existence. Instead, reality deepens. The universe becomes a gradual unfolding, a fractal story written over infinite ages. There is beauty in this vision. Even comfort. An eternal universe means creation is not a single miracle but an ongoing process. It means we belong to something that has always been and may always be. It means the cosmos is not a firework that flares and fades but a vast, timeless ocean whose waves take the form of galaxies, stars, and life. Yet there is also humility in it. We live in one fleeting moment of an infinite continuum. We are not close to the beginning because there was no beginning to be close to. We stand not at the edge of time but within its endless flow. And as we contemplate this possibility, a deeper truth emerges. Perhaps the universe is not asking us to find the beginning. Perhaps it is asking us to let go of the idea that beginnings are necessary at all. The universe has long been described as beginning with an explosion, a sudden, violent eruption that brought matter, energy, and spacetime into being. This fiery birth has dominated cosmology, shaping how we imagine the origin of everything. But what if the universe did not begin with a bang at all? What if its birth was not explosive but transitional, not chaotic but smooth, not a detonation but a transformation? This idea reshapes the earliest moments of reality, replacing the familiar cosmic fireworks with something far more subtle and profound. A universe unfolding like dawn rather than bursting like lightning. Imagine standing in darkness as the first traces of light appear, not in a blinding flash, but in a gentle glow spreading slowly across the horizon. The universe may have emerged in a similar way. Instead of erupting from a singular point of infinite density, it may have passed through a phase change, like water turning to steam or ice melting into liquid. Before this transition, reality may have existed in an unfamiliar state, with no particles, no forces, and no classical spacetime. Then, as conditions shifted, the universe gently transformed, smoothing into expansion without the violent bang we imagine. This perspective challenges one of the most deeply rooted ideas in modern science: the singularity. The singularity has always been a mathematical alarm bell, a point where equations break, where infinities appear, where physics stops making sense. A smooth origin universe avoids this problem entirely. Instead of starting from an impossible point, it begins from a physical process. This transition could resemble a cosmic boiling, a shift in the structure of spacetime itself, or a release of stored energy from an earlier, stable phase. In some models, the universe existed before this transition in a timeless, unchanging state of perfect symmetry. There was no direction to time because nothing changed. There was no expansion because nothing moved. Then, a delicate symmetry broke, perhaps triggered by quantum fluctuations, or by instability in a deeper field, or by a slow accumulation of energy imbalance. When the symmetry broke, time gained direction, space gained curvature, and the universe began to evolve. This emergence need not be violent. It could be as gentle as a whisper, as subtle as a ripple forming on an otherwise still lake. Other theories envision the universe emerging from a contraction phase, not in a bounce but through a smooth handoff from one regime of physics to another. Imagine a collapsing universe reaching a point of extreme density where quantum effects soften the collapse, preventing a singularity. Instead of rebounding sharply, spacetime transitions fluidly into expansion. The compression slows, stabilizes, and dissolves into a new expanding universe. No bang. No discontinuity. Just a cosmic exhale following a long inhale. This shift in perspective explains several cosmic puzzles that trouble the traditional Big Bang picture. The uniform temperature of the cosmic microwave background becomes easier to understand. In a smooth origin universe, regions of space could have interacted or equilibrated before expansion began. There is no need for inflation to artificially flatten or smooth the early universe. Instead, smoothness becomes an inherited trait of the pre-transition state. The apparent absence of early chaos also makes sense. The observed universe appears surprisingly ordered, with galaxies forming too early and structures arising too quickly. A smooth origin universe may have contained the seeds of structure long before expansion began. Rather than being created suddenly, complexity could have been embedded in the fabric of reality, waiting for the transition to activate it. Even the flow of time feels different in this framework. Instead of time springing from nothing, it gradually emerges from a deeper, timeless state. Before the transition, before might not even exist as a meaningful concept. Time becomes a property of the expanding phase of the universe, not a universal backdrop. It is similar to heat. It appears only when motion and interaction occur. The universe may have transitioned from a timeless existence to a temporal one, allowing time to take root and spread like light in darkness. This concept holds emotional weight. Without a bang, the universe loses its dramatic beginning, its cosmic explosion that births everything in a single instant. Yet, in its place we gain something even more profound. We gain continuity. We gain depth. We gain the possibility that the universe is not defined by abruptness but by transformation. Instead of a universe born screaming, we imagine one that opened its eyes slowly, emerging from quiet potential into radiant existence. These theories also dissolve the need for many problematic forms of fine-tuning. They eliminate the requirement for infinite inflation, exotic fields, and contrived conditions that must behave perfectly to match observations. A smooth origin universe feels more stable, more natural, more aligned with the processes we see elsewhere in physics. Of course, this new vision raises new mysteries. If the universe transitioned smoothly into existence, what was the nature of the pre-transition state? Was it quantum? Geometric? Something beyond both ideas? Did the universe contain information before expansion? Did structures form in ways we cannot yet imagine? The questions multiply, expanding like space itself. And yet, even in uncertainty, there is a strange comfort. A smooth origin universe suggests that creation is not an abrupt miracle but a process woven into the fabric of reality. It suggests that the cosmos came into being not with violence but with grace. It suggests that the earliest moments were not a blinding explosion but a cosmic sunrise, gentle, subtle, and filled with quiet power. As we explore this possibility, the universe becomes less like an explosion and more like a story unfolding through transitions. It becomes a tapestry woven from phases of existence, each leading naturally to the next. And in this woven story, the Big Bang becomes not a singular beginning but a transformation. One chapter in a much older, much deeper cosmic narrative. In the end, the idea of a universe without a bang invites us to rethink our place within it. We are not children of an explosion but of a transition. We are the inheritors of a cosmic dawn that began not with violence but with emergence, quiet, smooth, and profound. When a grand story breaks apart, it forces us to confront the vastness of what we never understood. The Big Bang once felt like a perfect origin, clean, cinematic, and absolute. But now, as new data contradicts its foundations, the certainty surrounding it dissolves. Stars appear older than the universe. Galaxies form far too early. The expansion behaves unpredictably. Dark matter remains invisible. Inflation collapses under its own contradictions. These are not minor details. They are fractures spreading through the heart of cosmology, telling us that our story of the beginning may be incomplete. Yet this collapse is not an ending. It is the doorway to a deeper search. Every scientific revolution begins by breaking an old pattern. As cracks appear in the Big Bang, new possibilities rise. Cyclic universes, emergent time, smooth origins, hidden eras before expansion. The universe becomes richer, older, and far stranger than the neat narrative we once accepted. The emotional shock is real. Humans crave beginnings. We want a first page where everything starts. Losing that comfort leaves us suspended in uncertainty. But uncertainty is where discovery lives. It invites creativity, courage, and a willingness to imagine beyond familiar boundaries. It forces us to question how we define origins, time, and existence itself. The universe continues on, indifferent to our confusion. Galaxies still shine. Light still travels across unimaginable distances. The collapse of the Big Bang does not unravel reality, it unravels our interpretation of it. And in doing so, it frees us to imagine a far more intricate cosmic history. This moment is not cosmology failing, it is cosmology evolving. The story of the universe is opening into a new chapter, one shaped not by certainty but by wonder. And in the quiet space left behind by the collapsing story, a deeper truth waits to be discovered. As the old cosmic narrative collapses, a new one begins to take shape, one woven from mystery rather than certainty. The universe no longer appears as a simple story with a single explosive birth. Instead, it feels like an ancient epic with hidden chapters, forgotten eras, and transitions far deeper than our first models imagined. The new story of everything must embrace this complexity rather than shrink from it. This emerging narrative suggests that the universe may not have one beginning, but many. The Big Bang could have been a phase change rather than a creation event. Time may have existed before expansion. Structures may have formed earlier than predicted. The cosmos may stretch back into eras that left subtle fingerprints on the sky, echoes of cycles, transitions, or quantum states preceding everything we know. In this new story, humility becomes essential. We must accept that the universe is older, larger, and stranger than our previous theories allowed. We must be willing to rebuild our understanding from the ground up, guided not by tradition but by the data that refuses to fit inside the old framework. This shift is both unsettling and exhilarating. We lose the simplicity of a single beginning, but we gain a richer sense of cosmic depth. We begin to see ourselves not as the result of one miraculous moment, but as participants in a universe shaped by processes that stretch across unimaginable spans of existence. Life becomes an expression of the cosmos's evolving complexity, not an accident of one explosion. The new story will continue to change as new observations come. There will never be a final version because the universe itself never stops unfolding. But one truth guides this transition: the collapse of the old story is not the end, it is the opening of a much greater one, waiting to be written.